Good morning. We can get started. It is my great pleasure to introduce today's IQUIST speaker, Kanu Sinha. So Kanu did her PhD at the University of Maryland on the theory of open quantum systems. Then she did postdocs at Innsbruck and the Army Research Lab, and then was a research scientist at Princeton before starting in the electrical engineering department at Arizona State University last year, and is now adiabatically transitioning to the School of Optical Sciences at the University of Arizona. So she's going to tell us today about atom-photon interactions in nanoscale quantum systems and waveguide QED.
Well, thank you so much, Elizabeth, for the introduction and for having me here. It's been a great pleasure to be here and to I've thoroughly enjoyed all the fun discussions and the hospitality. It's also I have to say, this is a nice break from the extended Arizona summer, which is still going on, but also in a way that it makes you appreciate the warmth when you go back. So yeah. All right, so I'm going to tell you guys today about atom-photon interactions in nanoscale quantum systems and waveguide QED. Let me first start with unpacking the title a little bit. So atom-photon interactions are the essential building block of pretty much all quantum optics, and they play an important role in several quantum information applications, as we all know. And also, as we all know, atom-photon interactions are very weak. So we need some way to boost them. And one way to do that is to shrink things down such that you can find your electromagnetic fields in smaller and smaller regions, and basically so that your atoms and photons can see each other better, which brings us to nanoscale quantum systems. Okay. And another thing, of course, that we'd like to do is to couple atoms or quantum emitters at long distances. And we know that in free space, interactions decay as 1/r³. So we need something like a telephone line between two quantum emitters, and that's what waveguides allow us to do. So you can build that way large-scale interconnected quantum systems of interest that way. Okay, so these are the kind of two regimes or systems that I'm going to talk about, one being the very small, the other being larger. And particularly in the context of nanoscale quantum systems, I want to discuss the effects of quantum fluctuations in these systems and how can we control them, how can we engineer them. And when we think about coupling two quantum emitters via waveguides, what I want to discuss is how do non-markovianity, or how do memory effects of the electromagnetic field come into picture there. Okay, so in the first part of the talk, we'll be shrinking things down, and in the second part, we'll be stretching things out to long distance, and we'll define what long distances mean in this specific case. All right, so nanoscale quantum systems are great because they give us efficient, tunable light matter interactions. Here's a few examples. And of course, these are just tourist cartoons, but the systems are very much real. They've been realized in various labs and by butterflies, even in some cases. It's the photonic crystal structure in the wing of a morpho butterfly, which gives it the cool blue color you can see there. They're also relevant to several applications in building single photon devices of various sorts, sensing gravitational fields, and many other applications. And in several of, and another reason, in addition to boosting light matter interaction, why do we want to shrink things down is because if you walk into a quantum optics lab, it looks like a jungle of big bulky optical elements, and you want to ideally shrink things down to the size of a chip. And as you do that, you inevitably run into atom surface interactions at nanoscales, and that's where we encounter quantum fluctuation phenomena, which influence how we trap our atoms, how these atoms decay, how they decohere, etc. So just to briefly define what do I mean by quantum fluctuation phenomena. So quantum fluctuation phenomena are ubiquitous in nature, from the atomic scale to pretty much the size of the universe. So if in case you're not familiar, well, so nothing is not nothing in QED. There's always quantum fluctuations or virtual photons coming out of nowhere and going back to nowhere. And these virtual processes have consequences which range from spontaneous emission and lamp shift to so what you're seeing here is the cosmic microwave background, and back in the early universe, the fluctuations of temperature in the CMB is what we know now to correspond to the density perturbations of how matter was distributed. So in some way, you can think maybe we are all quantum fluctuations, perhaps. Somewhere in between atoms and the universe, there are geckos. And the reason why geckos can walk on walls and support their own weight against gravity is because they have these teeny tiny hair on their feet called setae. And the van der Waals forces, the adhesion, is what allows geckos to climb on walls. And there's some interesting research in the field of biomimicry where people are trying to build gloves for humans to be able to climb on walls as well. So we may have gecko people at some point. All right, so these ideas, actually, just to give you a bit more historical context, the forces arising from quantum fluctuations go back to the 1940s. This is back in Phillips Labs in 1948, where the experimental group of Theo Overbeek was studying stability of colloidal solutions. So they were trying to explain why is a certain colloidal suspension stable. And what they observed is that there's a certain characteristic distance between two colloidal particles. And for that distance, if you use, let's say, the London theory for studying the intermolecular forces, you get a force that's much stronger than what would keep this colloidal suspension stable. So the forces should scale as 1 over r to the 7, not 1 over r to the 6. Or rather, the potential should scale as 1 over r to 7 and not 1 over r to 6. And Casimir and Polder wrote a QED description of interparticle interactions, including retardation effects of the electromagnetic field, which give you the correct scaling. And in a way, what it says is that retardation effects are necessary for explaining these particle-particle forces in the regime where they were studying colloidal suspensions. And also, you can think that if we didn't have a finite speed of light, we probably wouldn't have milk, because milk is also a colloid, among other things that we won't have. So this led actually Casimir to think. Allegedly, he was taking a walk with Niels Bohr, and Bohr mumbled something about zero-point energy. And then Casimir wrote his famous paper, which is just 2-page. Actually, there's just a little bit of a 3rd page as well. But the main derivation, it's a really nice paper. If you are interested, I encourage you to read it. The main argument here in this paper is that if you take 2 perfectly conducting parallel plates, you can write the sum over all vacuum modes, the zero-point energy of the modes contained outside and inside, in the presence of these plates and not. And the difference between these 2 energies gives you the attractive, it gives you the energy that depends on the separation between these plates. And a derivative of that energy is the force, right? So that's a very neat derivation. And to give you some idea of what the magnitude is, so for, say, some characteristic numbers of centimeter by centimeter plates separated by a micron, this is 0.013 dyne. That is a number I have no feelings for. So this is about 1,000th of a weight of a housefly, for those of you who don't know what that is. Okay, right. Now, Casimir forces have been studied, and typically when we discuss these vacuum fluctuation-induced forces, we think of two objects that are classical, so that have well-defined boundary conditions, spheres, plates, plates and plates, spheres and spheres, etc., and that are separated by the vacuum electromagnetic field. Now, what we are thinking about, going back to nanoscale quantum systems, is replace one of these objects by a many-body quantum system. So you have, a bunch of atoms, solid-state emitters. It could be a nanoparticle that is, delocalized here and there. And now this quantum system is interacting with some macroscopic body, which could be surface of a chip or a waveguide, via the quantum fluctuations of the vacuum field. And in this scenario, quantum fluctuations will lead to forces, dissipation and decoherence, which we need to control. But another important thing here is that we can use the quantum properties of this system to control quantum fluctuation effects, because we have an additional knob, and that's what I want to discuss today. To give you some idea of why or what's the magnitude of these effects, we can draw a very toy model picture of understanding what these effects scale like. So here's an atomic dipole at a distance z away from a mirror. So as the dipole stares into this mirror, you get an interaction potential due to electrostatic image charge theory, which should scale as 1 over z cubed, as we expect. This isn't the right, so we need some dimensions of energy here. So the only energy scale that we know as far as the interaction with the vacuum goes is h bar gamma 0. And this is still not the right dimensions. We need some length scale. And the only length scale we know here is the atomic transition wavelength, which is the only meter stick this atom has. And it's actually only a factor of 16 away from the ground state potential of a 2-level atom in the near field regime away from a perfect conductor. And if you plug in some typical numbers here at distances of tens of nanometers, this becomes 10 millikelvin, which is much stronger than our typical means of trapping particles. And you can see this more manifestly. Okay, so there's a box here actually, which kind of delineates the it's not very visible, but imagine there's a line here which shows that all these are the closest near surface traps that we have, and around 100 nanometers or below 100 nanometers, fluctuation forces dominate or overpower most of our ways of trapping particles. So we need to figure out a way how to control these forces, right? So how do we control these forces? That's indeed what we do. So we think of this in an open quantum systems perspective. So here we have our quantum system of interest, which is interacting with the field. And the density of modes of this electromagnetic field is modified by some boundary condition. As these system and the bass interact, we get all these fluctuation phenomena. And in this picture, what we can think of is we can do a few things. So we can change the boundary condition by changing the optical properties, material properties, or geometry of the surface. We can modify directly the system bass coupling. That's, for example, using magnetic interactions, which can allow for repulsion. The more quantum things to do are, for example, using an external drive to drive your system to some interesting non-equilibrium steady state. Or we can use entanglement within the system. Because it's a quantum system, we are perfectly well allowed to use interesting internal states, entangled states, and so on. And this basically combines, on the one hand, all the interesting Casimir physics phenomena that in fluctuation or QED phenomena that happen near surfaces, with different ways of trying to engineer quantum states in open quantum systems. And this sort of enables us to control quantum systems at nanoscales. And so this is not an exhaustive list, but these are some of the ways that we've looked at the problem of trying to engineer various quantum fluctuation phenomena in nanoscale systems. And today, I mostly want to focus on this story, and I'll tell you a little bit about our recent work where we are trying to engineer interparticle potentials using external drives as well. Okay, so using collective effects to control Casimir forces, first of all, what are collective effects? So collective effects have been known in the context of spontaneous emissions since 1954, thanks to Robert Dicke. And the idea is that if you have n emitters, each of which emits, independently at a rate gamma 0, you can prepare these in a super radiant state where the interaction between these dipoles and the electromagnetic vacuum is constructively enhanced, and they emit then with the rate n gamma 0. Or you can also destructively cancel the interaction between your atomic dipoles in the field by putting them in a subradiant state. Now, what if I take these collective atomic states and put them near a surface? The intuition here is that just using the analogy that Casimir-Polder interactions or Casimir-Polder forces are kind of like the dispersive counterpart of spontaneous emission, just like we have collective effects in spontaneous emission, we would also expect to see collective effects in vacuum forces. And indeed, that's what happens. So we can think of a toyest system possible where we just have two atoms, red and blue, near a surface, interacting with the quantum vacuum field. And if we look at the kinds of processes that happen between these atoms as they are in the super or subradiant state, which are, this state of the blue atom being excited, red being ground, in a plus or minus superposition with blue in ground and red being excited. You can imagine a process where these two exchange a photon, and the photon scatters off of the surface. So this is a resonant surface-mediated resonant dipole-dipole interaction. And these two processes can interfere either constructively or destructively, depending on the sign of this state. And that is what indeed allows for an enhancement or suppression of the total Casimir-Polder force, which we can see here. So just like we can write a gamma super and a gamma sub for the two atoms together, we can very analogously write a super or subradiant Casimir force. And here we are plotting an example of the case where we have two atoms for some typical numbers of, optical wavelengths, resonance transition frequency, sub-wavelengths distance away from the surface. And we can see if we prepare these emitters in a super radiant state, as we bring them closer and closer, their collective emission increases, and at the same time, their Casimir attraction increases as well. On the other hand, if you prepare them in a subradiant state, you can see this is nice because we can have them, we can have their decay rates be smaller, but at the same time, reduce their attractive Casimir force, which is nice to have because then perhaps we can, trap particles near surfaces using this way. And to focus on this a little bit more closely, here we can look at the subradiant Casimir force on these two atoms as well as the gamma. And for two emitters that are about a couple of nanometers apart and 10 nanometers away from the surface, we see that you can have reduction in both the gamma and force up to a factor of 100, which is potentially nice to have. In terms of proof of concept, one can imagine that if we take a nanodiamond, which is embedded, for example, with silicon vacancies, and you excite all these emitters first to an all excited state, and as these go towards the ground state, one would see the super radiant emission both in terms of gamma, but also an enhancement in the force that this particle as a whole experiences. So if I were to put this on a cantilever, you would expect to see a boost of, about tens of femtonewtons for about 10 or 12 emitters that are behaving cooperatively in this case. Okay, so just to summarize, the first part here, what I've told you is that fluctuation forces can be modified via preparing quantum emitters in collective states, which we can understand as a constructive or destructive interference in the surface-mediated resonant dipole-dipole interactions. Currently, we are working on some exciting questions. There's this experiment in Paris by my colleagues there, Gabriel Dutier, who's the lead PI, and what they're looking at is what is the so they're considering atomic beams going through a diffraction nanograting, and when you look at the diffraction pattern, so this is actually the experimental data over here. You can see that it contains signatures of the atom grating interaction. And this is a very interesting problem because, well, on the one hand, we can excite the atoms before, prepare them in whatever states we potentially want. But also, this is a very, very much an example of a situation where you have one object that is solid, but on the other hand, the other Casimir plate is diffused kind of all over the place. Okay, so this goes back to the idea of doing Casimir physics with quantum objects. Another experiment that I'm currently collaborating with in Vienna, this is in the group of Marcus Aspelmeyer there. You cannot really see the tweezer beams. There's two tweezers that are trapping these particles. It's not just held in vacuum. I mean, vacuum helps. That's what we're trying to claim. But yeah, there's also a laser here. So in 2020, there was this very nice work where they illustrated ground state cooling of a levitated nanosphere of about 100 nanometer radius. And since then, they've been exploring interactions between two nanoparticles, which is what we are working on together. And the idea is that as you bring, two levitated nanospheres closer together, these fluctuation-mediated interactions start to become prominent. And what we've been able to demonstrate so far is that using external drives and other interesting quantum states of the field, one can create mutually bound potentials for two nanoparticles that can be up to 200 Kelvin deep or so. So this is something we are excited about and hoping to see this in the lab in the next few years. All right, so when we were looking at this idea of collective Casimir-Polder interactions, around the same time, there was this experiment by my collaborators in Maryland. And this was great because what they observed was super radiance and subradiance near in a cloud of atoms near a nanofiber. And what you're seeing in the picture here, so this is a atomic cloud, a MOT. And one of the things they did in this experiment was to split the cloud into two subclouds and then observe the collective emission then. And what they saw is that the collective emission doesn't change, which is what led them to conclude the title of this paper, that superradiance reveals infinite range dipole-dipole interactions. And when we started discussing this, we kind of got hung up on this title and we started thinking, does it really? So what if you take these atoms really, really far apart? So that brings me to the next rabbit hole that I'm about to jump in. So also, what is really, really far apart in this case? So what we started thinking about is, say you have two atoms that are coupled to a waveguide. So this is, again, a very toy model picture of the whole scenario. And each atom emits into the waveguide at a rate gamma. There's some velocity with which the photons travel in the waveguide. And what if we separate these two atoms, or whatever quantum emitters these might be, by a distance v over gamma, where this corresponds to something like a length scale or a coherence length that you can associate with the emitted photons, okay? And what we can see is that at such long distances, the memory effects of the field start to kick in, making the system non-Markovian. And in case we don't remember what non-Markovian is, let me refresh our collective memories, which is, so when we think of the open system dynamics of a quantum system, this is a quantum system interacting with a bath. What we typically assume is that the correlations of the bath decay much faster compared to the time scales of the system dynamics, such that the system doesn't have any previous memory of its dynamics, okay? And when does this start to change? So here in this situation, when we have two subsystems, 1 and 2, we can we know there's a time scale associated with the bath to go from one system to the other, which is d/v. And there's a time scale associated with the system's own relaxation dynamics, which is 1/gamma. And we can make a simple dimensionless number ratio, gamma d/v. And for the bath time scale to be much, much smaller than the system relaxation, this number should be much, much less than 1. Okay. And if that's not the case, then we start to see non-Markovian dynamics or some memory effects. So you can, for example, if you have slow bath modes, you can imagine that photons are lingering around the system for longer than they should, and they remember more. Or if you have strong coupling, then again, you have a coherent exchange of information and energy, and that too makes your system non-Markovian. And what we are thinking about is a large D situation where we have retardation. And of course, these effects have been studied previously by other people in strong coupling regime and structured reservoirs. And there's good reasons why we want to study retardation effects from also the perspective of, when we're trying to couple quantum emitters for building quantum networks or doing distributed sensing and metrology. We need to think about these kinds of systems, but not just that we need to think because these effects are relevant, but they could potentially be useful as well. So that it has been shown, for example, that you can use delay to generate photonic cluster states or long distance entanglement, which is something I'll also mention later. Okay, so how do we understand this? It's actually, again, a very simple toy model to think about. We can go back to now two level atoms as before, coupled to a waveguide. And we are preparing them to start with, let's say, in an initial state that is either this EG plus or minus G, okay? And as these atoms interact with the waveguide, there's some emission into the waveguide, which I'm calling gamma 1D, and the outside is gamma 3D. So as the system evolves, I have very little math in this talk, so I hope you'll bear with this, but there's a point you'll see to writing this. So as the system evolves, we can, given the initial condition that we've assumed, we can say that there's either one excitation in atom 1 or atom 2 with some probability amplitude C1 or C2, or there's one photon somewhere in the waveguide with some probability amplitude CG omega. Now we can eliminate the field to write the coupled equations of motion for the two atomic amplitudes, and it's pretty intuitive. So as you can see, the first part indicates how each of these atoms emits spontaneously into the waveguide, and the second part gives you the delayed kick of the other atom on the first or second, which comes with how efficiently these atoms couple to the waveguide, and what's the phase of propagation for the field to go from one to the other. And this is actually a fairly ubiquitous set of delay differential equations, which appears in many kinds of systems, from population dynamics to ADS-CFT correspondence. So we may as well be talking about rabbits and foxes and prey-predator dynamics. The quantization and phases there are slightly different perhaps, but yeah, the essential dynamics is fairly universal. So we can solve this. This has been well studied and known. And what we understand from this solution is, so we see there's a series, and this series represents the multiple times photon wave packets go between the two atoms. So we can now reimagine or think of collective emission from a couple of atoms as a series or cascade of mutually stimulated emission, looking at this. And in particular, if we focus on the time when the atoms first see each other, we can clearly see that there's the spontaneous emission before they interact. And then once the light from one atom reaches the other, there's a modification to that exponential decay, which is what makes it non-Markovian. And in particular, if you look at the super radiant state, we see that the rate at which this decays now can exceed 2 gamma, which is what I'll talk about in a bit more detail. But if you're in a subradiant state, this can be negative, meaning that the information can potentially come back from the bath to the system. So to look at the decay in more proper terms in a picture, here we are plotting the decay of a super-radiant state for different separations between the two atoms. So I'm varying this dimensionless distance from 0, which is this the blue line with 2 coincident emitters. The black dotted line is the 2 emitters that are infinitely far apart. And if we pick one of the distances in between, so for example, eta equals 2, the teal line, so that coincides with independent emission until the atoms see each other, and then they decay faster than regular super radiance. So this is an effect that we call a super-duper radiance, in fact. So the reason for that is because ultra radiance and hyper radiance were taken by other people, so that's what we are stuck with. Right. Now we can also look at this from the perspective of the field. So what I'm plotting here is the light cones that are emitted by each of these two atoms that are sitting over here somewhere. And you see that as the light cone of one atom hits the other, there's a stronger emission going outwards, which is what we've been referring to as super-duper radiance. More interestingly, though, we can look at the case where the two atoms are in a subradiant state to start with. And here, as the atoms first see each other, they start behaving as perfect mirrors almost. So now the photons, stay trapped in this cavity that's being formed by the two atoms. So it's kind of a cavity made by the atoms for the atoms, the democratic cavity, if you will. And it's a very interesting idea to me because there were some recent experiments. This was a circuit QED experiment from the group of Oscar Painter, where they observed a subradiant atomic cavity. So this is not, science fiction, but it's been realized. And also this year, there was this experiment with a Rydberg atom array from Johannes Seiher's group, where they were able to switch an array of atoms that was behaving as a mirror by using an external Rydberg atom as a switch. Well, the Rydberg atom also was in the same array, so it's not as external, but the idea that you can have a collection of atoms or a single atom behave as a mirror is very much been realized. So this led us to think something that we are currently working on. This is work in progress, but I did want to share this. So you can now consider a situation where you have a 3-level system, and I can put, so there are 2 ground states, G and G prime. And if I send in a photon, which is resonant, let's say, with this transition, omega 0, at the same frequency, this state, the state G, acts like a mirror. On the other hand, if the atom was in the state G prime, it acts like not a mirror, okay? So now it inspires us to think some crazy questions, which is that what if I start putting my atoms in superpositions? What does that mean? And that is indeed what we're doing. So currently we are exploring, so this is with my students, Anyun and Jenny, we are exploring these questions of, say you have an excited atom in front of this quote unquote mirror atom, which can be prepared in different states. And let's say if I prepare this mirror atom in a state G, we see again a cavity-like effect as we did in the previous case. But now the cavity is leaky, as you see, so that the photon eventually leaks out because of the fact that the excitation will eventually go to G prime, and then that level doesn't really form a resonant cavity with this atom. Yeah. If we put this atom on the other state, G prime, we see there is no cavity effect. This is just, you know, spontaneous emission of this atom. That's it. More interestingly, we can put this in a superposition of G and G prime, where we see a couple of things going on. So one, there is something like a cavity, but there's also some quantum beats that you notice on these are the stripy lines on the y-axis, which is the beating between the two omega 0 and omega 0 prime frequencies. So this tells us that, well, we can make something like a mirror or a quantum mirror, if you will, using these 3-level atomic systems. So we made a quantum cavity, and we ask a question where we can put an atom in an excited state in between these two quote unquote quantum mirrors, where we can prepare these mirror atoms in potentially a superposition of being in a mirror-like state or a not mirror-like state. And what this shows us, so if in particular, if we turn off the G prime E coupling, which I'm told can be done by Elizabeth, then we can see that the dynamics that follows is something like a superposition of a atom decaying in a cavity and an atom emitting spontaneously. So there's interesting questions, you know, to be asked there. What happens when you make one mirror and one atom as mirror and the other one as not in a superposition with other kinds of mirror, not mirror states. So we are exploring all these questions at the moment. So, all right. So now going back to actually what we started this whole story with, which is, are dipole-dipole interactions infinite ranged when two atoms interact via 1D? What we find at the end is actually that's not the case. So there is a rangedness coming from the non-Markovian effects of the field. And this is something, you know, that gives you a finite finite range of interaction for two emitters that are very far apart. Okay, and this is all good. You can also ask, what is this good for? And one thing that we've seen so far is that you can think about two emitters that are prepared in excited states, very, very far apart again. And if they're both excited, as they each decay into the waveguide, they land into something like an entangled state. You can't quite see, maybe this is a very faint entangled state here. And this is due to, in fact, the non-Markovian nature of the interaction. We can see if you didn't have a significant enough delay, this wouldn't happen. So here, for example, what I'm plotting is the separation between the emitters in dimensionless terms again. This is the phase of propagation. So you need a specific phase of the field to reach this entangled dark state. And on the z-axis, this is a quantifying the atomic entanglement in the steady state via concurrence. And we see that you need a significant enough delay of about, this eta parameter or the distance between the atoms should be roughly 0.9 or 0.895 of the coherence length of the photons. So that's interesting because here we are not doing any heralding or post-selection, but the atoms on their own are landing into this entangled dark state. You can also ask what kinds of experimental situations exist where we can see this. There are a few. So one that's that we are currently exploring and interested in is the one with, again, atoms coupled to optical nanofibers. This is an extension of the previous experiment now with 2 nanofiber sections where we excite the atomic cloud from the side and then hope that there's few atoms here and few atoms there that will land in some correlated state. And then when we observe the emission, there will be some signatures of collective non-Markovian emission. As we were doing this, we ended up finding something else along the way and got distracted a bit. But what we found was something, was a signature of quantum beats induced by vacuum. And the idea here is that, so this is rubidium-85, that was the atoms that we were using. And we were exciting this to one of the excited levels, 2, here. And what we saw in the emission was beats, which we totally did not expect because we were not exciting this to the other level at all. However, what happens is that there's a vacuum-induced coupling between these 2 levels, which can allow you to see beats. But because it's a vacuum-induced coupling, it's very weak. So you won't see it unless you have some collective enhancement. So what we saw eventually in terms of the measurement was vacuum beats that were collectively enhanced, and we could explain it theoretically nicely. So you can see the nice solid theory curve, which lines up well with the data there for different optical densities of the atoms. So we were happy with that. And now we are back to trying to explain what collective emission comes out of the system. Of course, there's a lot of details to do with atomic motion, which we are currently, trying to understand and deal with in this experiment. And yeah. Another, how much time do I have? 10 minutes? Oh, okay. So I think I'm well on time. Okay, so one last idea that I wanted to mention here is this situation where we can think about making photon velocities direction dependent somehow. And we call this anisotachy. This is a made up word, which is aniso meaning different in different directions. Tachy is speed, so different speed of light in different directions. So what we're doing here is we are coupling these atoms to waveguides with 2 circulators in between that are in turn coupled to 2 different kinds of waveguides or different length of waveguide. And what you can have is that when light goes one of these ways, you have a different medium along the way, and as a result, a different velocity. And if the photon goes on the right, you take the bottom path, and as a result, you have a different speed of light going the other way. Now, in this situation, we can again imagine that since these velocities are different, it's very much possible to have different path lengths. And if we have different path lengths, what we can do is we can make one of these atoms emit super radiantly and the other one subradiantly. And that is exactly what we see. So we can plot now the dynamics of these 2 atoms, and we see that there's a different time at which the 2 atoms start emitting collectively because of the fact that they don't see each other at the same time. And then one of them goes subradiant, that's the blue one, and the red one goes super radiant. And at later times, this behavior reverses as the phases interfere differently each time. This also you can see in the slide cone picture. So when atom 1 sees atom 2 over here, it goes subradiant and reflects the light. And when atom 1, or when the light from atom 1 reaches atom 2, it's super radiant. So it's basically giving you a directional emission as a result. And this is neat because we can characterize the directionality of the emission by some, directionality parameter, which is to say how much light goes left to how much light goes right, depending on what's the initial state of the atom. So this is this theta and phi s. These basically characterize some initial atomic state, which is potentially entangled. And then there's a propagation phase associated with the light propagation between the two emitters. And what we find is that this asymmetry of whether the photon goes to the left or to the right depends on what's the initial state, what's the path length, and any other parameters that may change or affect that. So in a way, it can detect, it can sense some path length or frequency length differences, potentially. Another thing one can imagine is that in such a system, if we send in a directional photon, we could, in a time reversed way, create entangled states, potentially. Right. There was a similar experiment done at Will Oliver's group at MIT, not with different velocities of light, but using a very specific initial state, which is the central points that you see here, where there's no anisotachy, as we call it. All right, so with that, I will summarize what I've told you here. So non-Markovian effects modify collective spontaneous emission at long distances. We can look at interesting atomic systems behaving as mirrors and forming cavities that can potentially be in superpositions of, cavities being cavity and not cavity, and so on. And some other things where, you can use non-Markovianity to generate entanglement at long distances. There are limits to dipole-dipole interactions in 1D and also to cooperativity, which I haven't discussed here. Currently, we are exploring a number of questions that follow from here. So this is these are questions you may also have, and I have the same questions. In particular, one idea in terms of what are these systems good for is, can we use non-Markovianity or the memory effects of the bath to enhance how one can sense, let's say, any parameters in the environment? So you have some additional degrees of freedom now to play with in terms of applications for sensing. And what I'm also very excited about is experimental demonstrations and this idea of making atomic mirrors a quantum. All right, so with that, I'd like to thank you all for your attention and my awesome collaborators, and I'm happy to take any questions.
All right, do we have any questions here on Zoom? I may. Chris?
So I think you had this up at the very end. So our patients sort of have two atoms juggle looking for
Oh yeah, so all that is super interesting to me. It's not analytically tractable anymore, it so happens, but nevertheless, that's the kinds of questions we are exploring at the moment with, so one of the problems that I mentioned, this one, here we do have two excitations, and the intuition that I have for why you need a delay to form this entangled state is that you need a characteristic amount of time for one of the atoms to have decayed to some amount where it can start, where it's not saturated anymore. So you need that delay length in order to, be efficiently interacting with the photon that's emitted from the other guy. But yeah, so I don't have a good answer as to, what do we expect when we go to multiple excitation. So some interesting nonlinear effects is what I can say at the moment, but yeah. So That would be very interesting. Yeah, we should talk more for sure. Yes.
Here, the wave, still longer than the wavelength.
Oh no, much longer, much longer. So the distance is comparable to gamma over V, and wavelengths would be more like omega 0 or the transition frequency over V. So this is about a ratio of the wavelengths to gamma. Yes. Oh yeah. Right. Yes. Thank you. That's wrong. So this is V over gamma. Yes. Okay. Bad typo. The V over gamma, and yeah, that makes sense because omega is much greater than gamma. So as a result, so for atomic systems, that would be optical to megahertz ratio.
So this was going to be all one-dimensional, only interact with the. Right?
Oh, so yeah, we do. Great, thanks for asking. So the pictures I showed you were for the cases where we assumed perfect coupling, but we can certainly assume imperfect coupling, and we can allow for emission outside as well. Right. You would, it would be weaker. So what happens, so great question. If I go back to I had the coupling parameter in the equation. So this beta is your coupling efficiency to the waveguide. So if you have, with each successive emission, so what I'm still assuming though, is that the waveguide is lossless, but each atom, when it interacts with the field, there's a possibility that it can scatter outside or into the waveguide. So if assuming that the photons do propagate losslessly over tens of meters, then this coupling efficiency enters and it makes the interference less constructive or less destructive. Right, so here we don't expect any collective effects via free space. So we are assuming all collective interactions via the waveguide. Mm-hmm. Thanks.
Any last questions before we